Hello, everyone. My name is Dr. Jacqueline O'Connor. I'm a professor of mechanical engineering, and it's a real honor for me today to be guest lecturing in Philosophy 133N, the ethics of climate change. I was really intrigued by this course, and so I'm very excited that I'm able to come to you. My great hope is that you won't have to use this video, that that aviation, which is what we're going to be talking about today, is going to get me to the Atlanta airport on time, and so that we'll get to speak in person. But just in case, your professor asked me to run through the presentation on a video, and then we'll have a discussion live afterwards. So I'm on sabbatical this year, so I'm coming to you from Charlotte, North Carolina. And I'm working at a place called the Electric Power Research Institute, which is kind of a neat place. We do research to support the electric power industry. But a lot of my research also focuses on sustainable aviation. And so that's what I figured you probably had a closer tie to. I think everybody uses electric power, but people have much less of an idea of how it's made and how it works than they do how an airplane works, because you you really get a very visceral experience every time you get on an airplane, right? It's loud, there's acceleration, you're up in the sky. Whereas when you flip a switch on or turn your stove on, it's not really that exciting an experience, or it should be an exciting experience. That means that it was a successful experience. So today we're going to talk about sustainable aviation and some of the climate issues associated with it. So first, I'm just going to give a brief personal introduction, like who am I and why am I talking about sustainable aviation? We're going to give some overview numbers of what role aviation plays in driving climate change. We'll talk about the variety of solutions for decarbonizing aviation. There are a number, but the one that people, I think are going to be the most successful and the one that's moved the farthest is on sustainable aviation fuel. So we'll talk about that. And then we'll finish off by talking about what is Penn State doing in this area, because it turns out we're doing a lot. All right, so like I said, I'm now a professor of mechanical engineering here at Penn State, but I was born in 1984 in Connecticut, and I've been an aviation nerd since 1987. The picture in the top left is a picture of me at age 3, the first time that I got on an airplane. And I think a combination of my endearingly pushy mother and my 3-year-old cuteness got me a seat in the cockpit. And I think I've been excited by airplanes ever since. I did undergrad at MIT, have a degree in aeronautics from there, and did my master's and PhD at Georgia Tech in aerospace engineering in Atlanta, Georgia. Afterwards, I did a quick stint out of aviation. I actually worked in piston engines, like large truck engines, at Sandia National Laboratories in California, in Livermore, and then came to Penn State in 2013 and have been a faculty member there ever since. Like I said, I'm currently on sabbatical as visiting scholar at Emory, but will be returning to Penn State later in the academic year. All right, so this is how I got to where I was. I decided when I was 8 years old that I was going to go to MIT, that I was going to, at the time I was going to study astronomy because I wanted to be an astronaut. But then my very helpful grandfather told me that engineers make more money, and so you should be an aerospace engineer instead of an astronomer. And that's what I've been ever since. The reason I'm a mechanical engineering professor, however, is because my area of research just happens to fall in mechanical engineering here at Penn State. There's, very little substantive difference between the two areas when you're studying as a student. Okay, cool. So that's who I am, why I'm interested in aviation. Let's talk about aviation and climate change. So this is a breakdown from the IPCC report on greenhouse gas emissions by sector. And today we're going to be focusing on transportation, and transportation, well, some parts of transportation fall into what people often refer to as the hard to decarbonize sectors. I would posit that personal transportation, like your cars, are not hard to decarbonize. I just bought an electric car, and drive a hybrid as the other car. But airplanes, for reasons that we'll talk about today, are very hard to decarbonize. And so, or at least they're very hard to electrify. And so transportation, that 14%, is where aviation falls. And like I said, I'd argue it's hard to decarbonize. If we now break out transportation, so this is again from that IPCC report through time, what you can see is that most of the carbon emissions are coming from road. And that includes, everything on the road, cars, what are called mid-class trucks, like, your UPS delivery vans, as well as the heavy, Class 8 trucks that are pulling freight. And in the green right here is, the dark green is domestic aviation, the orange is international aviation. And so together it's making up almost, I don't know, let's say a little over 10.5% of the transportation emissions. That's about 2% of the global emissions. So on the whole, we're not producing a crazy amount of CO2 from aviation. However, what is happening is that a lot of these other sectors are being decarbonized rather quickly. And if we don't keep pace in aviation, we're going to start to stick out like a sore thumb. There are other issues, which hopefully we can get to in our discussion, that are sort of special about aviation, because we're flying in the sky. We can actually affect weather. We can affect cloud cover. And that certainly raises questions about not just our CO2 impact, but our climate impact more generally. All right. So that's where aviation falls on the climate spectrum. Let's talk about what we're going to do about it. And if you really want to understand what very smart people are thinking about, there's a really excellent National Academies report. Actually, the co-chair of this report is a professor at Penn State. Her name's Dr. Karen Tolley, and she's amazing. She is a colleague of mine who also works in sustainable aviation, but this gives the real details about what the promising technologies are for decarbonizing aviation, particularly commercial aviation. If you're not a STEM major, this report's going to be a little overwhelming, but there are some good charts in there and some details that if you are a STEM major, I encourage you to read. The report outlines 4 approaches, and these are the approaches that most folks think are going to drive decarbonization of the commercial aviation sector in different amounts. The first one are sustainable aviation fuels. That's what we're really going to focus on today. If you look at this projection, this is more of an industry-based projection, not as much an academic-based projection. You can see that technology improvements account for 22% of the reduction. Operations, 10%. So that's like how much time you're spending circling the airport before you land, how you get off the ground, that sort of thing. That's operations and infrastructure. But a whopping 61% is going to come from the fuel you use. And industrial sources right now, that's, airlines, people who make engines and airplanes, are generally pointing to sustainable aviation fuels as the way that we're going to get there. People have other ideas, though. There are a few companies focusing on hydrogen as a fuel. There are two in particular. One in the United States is a company called Universal Hydrogen. The other one, I believe, is French and is called Zero Avia. Both have flying demonstrations. Actually, Universal Hydrogen just got a permit from the FAA to start testing out in the Mojave Desert. And they have fuel cell powered airplanes that hold, 4 people where they're testing this technology. It's a long way out, but people are considering it. There are real questions about how big you can scale it to large passenger aircraft. The next one is hybrid electric. Just like you could hybridize your car, you could hybridize your plane. There are a lot of questions about how much that's actually going to help, and some recent research that suggests it's not a lot. And then fully electric, you're not going to fly across the Atlantic Ocean on a fully electric airplane. You can do the thermodynamics, pretty simple analysis to show that that's physically not possible. with current battery technology, or even optimistic future battery technology. But you could do small planes, right? So hopefully someday you'll be able to fly a shuttle flight from New York to Boston, let's say, on an electric aircraft, and that'd be okay. So these are the technologies, but like I said, we're going to focus on sustainable aviation fuels because this is what people are working on now. And to be perfectly honest, in my expert judgment, this is what's going to get us there. So Penn State has a lot of expertise in sustainable aviation fuels, and we're going to talk about more of this at the end. But this is a whole of Penn State approach, right? Actually, some of the best work in sustainable aviation fuels is happening on the feedstock end in the College of Agriculture. There are people looking at how to make the fuel and then also how to integrate it into aviation. And so these are centers, research centers, and colleges that are doing this type of work. So there's a lot of really exciting stuff happening at Penn State. Okay, so I love this chart. It's a little bit of a spaghetti chart, but I think it really shows what's going on. So on the left are fuels. And this is, again, this is from the IPCC report. This is how much energy we're using in exajoules, right? So very, very large amounts of energy. And these are the different fuels that are going into different uses. So heavy road transport, that's like freight trucks. Light road, that's your car, air travel, and then rail. And then you can see we've broken out transport by freight and passenger, which are also almost equal contributors. Oh, and then there's water, which is marine, right? So ships, barges, that sort of thing. And then the fuels that go in. So if we focus on air here in the middle, so the way to read this chart is to start in the middle. We say, okay, where is the fuel coming from? The vast majority of the fuel is coming from heavy oils, particularly kerosene. That's, the fancy name for jet fuel. And just smidges are coming from other sources of fuel. This is the gasoline and diesel are mostly, personal aviation. Your little Cessna that you'd fly to get out to an island or something. Breakdown, most of this is passenger, so that's really what we're focused on today, but everything we learned for passenger can also go to freight. The important picture here, though, is the mechanical energy versus the losses. This is thermodynamics. You can't completely convert heat to work. The second law doesn't let you do that. The heat here is the fuel. The work is the mechanical energy to push the airplane forward. And you can see that the efficiency here, which is the mechanical energy over the total amount of energy that you're putting in, isn't great, right? And so this is where a lot of those technology improvements are going to help. But the second law of thermodynamics is you can't derive a perpetual motion machine. It's not going to get you all the way. So we also need to think about how we're going to replace this fuel. So that's where sustainable aviation fuels come in. All right, before we talk about sustainable aviation fuels, it's important just to talk about aviation fuels. So what is jet fuel? If you put on your chemist hat and you looked at what jet fuel is, it's a bunch of hydrocarbons, which are molecules that are made of hydrogen and carbon. They come in different shapes. We don't have to go over the shapes, and they come in different sizes. So that's the carbon number. So how many carbons are in the hydrocarbon? It's sort of a mid-range. It's heavier than gasoline. It's lighter than diesel. So if you were going to put on your academic chemistry hat and you said, what is jet fuel? You'd get a picture that looks like this. However, if you were going to put on in real life, what is jet fuel? Jet fuel is not specified by what's in it. There's no rule that says just jet fuel has to have a certain amount of whatever molecules. There's an ASTM standard that tells you what jet fuel is. And so this unreadable chart on the left, and here the letters are very small for effect, tell you what jet fuel is. Has a particular acidity. It has maximum amounts of some molecules. So aromatics, which are these ring-like structures, these make soot. They're not good for people. They're carcinogenic. So we put a cap on the amount that you can have in. Sulfur, again, not great for you. So there's a cap there. But then how well does it boil, right? Or evaporate? What's its density? What's its viscosity? How much energy does it have? How fast does it corrode the parts, the tank that it's sitting in? All these things are what make jet fuel. And it goes through a very complicated series of tests in order to get there. All petroleum-derived jet fuels have been through these tests, and now refiners can make the jet fuel and they don't have to go through the test again. So then what is sustainable aviation fuel? Well, sustainable aviation fuel has to meet all these same criteria, right? You got to drop it in the same tank. It has to be used by the same engine, but it comes from a different source. And recently the FAA has said that sustainable aviation fuels have to reduce the carbon impact of burning jet fuel by at least 50%. Doesn't have to be 100% renewable. It has to be 50% less carbon intensity. They can come from a bunch of different places. And so these sort of 4 points here are the different molecules we were seeing before. It's really easy to make some of these molecules isoalkanes. We have a whole bunch of different ways of doing that. It's very difficult to make cycloalkanes, but they're really useful molecules. So there's still a lot of stuff under development. Right now, you can only put a maximum of 50% sustainable aviation fuel in your airplane. The other 50% needs to be petroleum derived, except if you're on like a test flight, because we don't have the confidence yet that all these things are being met. And for very good reason, the aviation industry is very safety oriented, right? When planes fall out of the sky, it's a really bad day. So we're working on it. And there are a lot of people, including people at Penn State, that are working on all these acronyms. These are different ways of making fuels. They have different sources. So here's a fun graphic I got from BP. And this basically shows where it comes from. Most of these input processes, all these bubbles up here, HEFA and FTSDK and, all that stuff, has a lot of different things you can put in. A bunch of them are wastes. So agriculture wastes, waste oils. So like cooking oils from McDonald's, like fry oil, you can turn that into jet fuel. Animal fats, what are you going to do with the rest of the animal when you turn it into food? You can turn it into jet fuel. Municipal solid waste, so basically garbage, can become jet fuel. Crops, you can grow crops like some cellulosic crops or some seed oils to become jet fuel. Or you can grow a crop, you can turn it into an alcohol, particularly ethanol, and then you can turn ethanol into jet fuel. That's a pretty well-established pathway. And then some folks are looking at growing algae. This is not done on any meaningfully large scale because algae right now, it's a very finicky little animal. It's difficult. Or plant? Is it a plant? I don't know. Anyway, it's difficult to grow in large quantities to make it meaningful as a feedstock. So anyway, this is where all these things could come from. And hopefully in our discussion, we'll have a number of discussions of the pros and cons of all these different sources and turning them into jet fuel. So why does fuel composition matter? Like, why can I only put 50% in? Well, it's obviously because it's the energy source, right? There's a lot of very complicated stuff happening in the combustor. This is my area of expertise, combustor fluid mechanics and combustion. You need the fuel to do the same thing, regardless of what it's made out of. Because when the flame goes out, particularly when you're at 40,000 feet, it's a bad day. And so, you need it to perform the same in the combustor. But then it also has to interact with the airplane. So this is an interesting picture from Boeing showing you where the fuel is in the airplane. There's a bunch in the wings and then a bit in the tank, in the tail, sorry, a tank in the tail. It's got to interact with the materials of the airplane. It's actually used as a hydraulic fluid. Before it even gets to the airplane, it has to sit in trucks, and be delivered in hoses. And before that, it has to sit in tanks and not separate. That's a big problem. And so the storage and handling and interaction with people, even before it gets to the airplane, all have to be considered when you're trying to certify an aviation fuel. So this is the combustion slide, and I won't talk through a lot of the details, but there are a lot of, if we have some STEM folks in the class who want to talk more, I'd be very happy to, but there's a bunch of really important stuff happening inside that engine, all the way from, is the flame in the combustor? That's what most of these top data show, to how does it spray, right? We got to spray the fuel in. Is it spraying the same? And then is it creating the same emissions? all these different letters, the things that start with A's and C's, those are different jet fuel types that mimic different types of renewable or sustainable aviation fuels. And the real point here is that these numbers are not the same, right? And so depending on the blends, depending on how you make it, right now there are differences, and we're trying to understand as a research community, does it make a difference? All right, so what are we doing about it? There's a lot of research that's happening that's funded by the US government, that's funded by the European government, that's funded by individual aircraft engine companies and aircraft companies, and we're working really hard to figure it out. What are we doing at Penn State? We do a lot. So like I said, we have a lot of expertise in fuel feedstocks and synthesis, particularly anaerobic digestion. So the folks over in the College of Agriculture and Agricultural Engineering are doing excellent work on figuring out what are we going to make it from and how are we going to make it. Once we've made it, then there's some really exciting work happening in how do we burn it. In particular, we have a lot of expertise in particulate emissions. So this is some data from my lab, different fuels, and how they burn and how they soot. And some folks over, particularly a professor named Randy Vanderwall, is one of the foremost experts in soot morphology and how it forms, particularly for aviation applications. We're trying to make engines more efficient, right? So even if we have a good fuel, we can boost our efficiency by working on the engine itself. And there are a couple labs at Penn State, particularly the START lab and the Excel lab in mechanical engineering, that are working on that. And then, we can make things even better if we can make them hotter. And there are people working on both high temperature ceramics as well as really unique high temperature metals that are allowing us to get to higher efficiencies and just make the engines last longer, which is also important. So hopefully you found that interesting. I also hope that I don't have to use this video, but I'm looking forward to our discussion and talking about some of the ethical implications, particularly on sustainable aviation fuels. But anything you want to talk about at this point, I'd be excited to talk about. Thanks so much.